Hello? Okay, perfect. It works. Welcome to United Astronomy Clubs of New Jersey. And thank you for everyone who's joined us here on site in Jenny Jump, New, in Hope, New Jersey. And also thank you for those who join us online because, yes, we do live stream this for on YouTube and Twitch. So while I see a couple people making their way down, a couple reminders, do check us out on our website, uacnj.org. That's where you're going to find a whole list of our member clubs and information about them, as well as information on our mission to bring astronomy to everyone we can. You'll also find a list of all our talks, upcoming and past, so you can go check them out. And if you ever see one that you're like, oh man, I really sad I missed that one, you can always check out our YouTube where we archive those talks that we've had online. And, if you have any questions about those talks, do drop those in the comments. And if you're watching the live stream, do like and subscribe so you get notifications when we do go live and you can't make it up here. That being said, you can also check us out on our socials. So Facebook, Instagram, Twitter. We'll be posting information on any special events or other interesting things that come up to do with astronomy and space. So tonight's talk is Bang, Woosh, Zoom with Paul Fischer. Paul has a Bachelor of Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in environmental and chemical industries. Though always interested in celestial objects, Paul's official start in astronomy was one night 7 years ago, lying in awkward positions on his roof in the freezing cold. Oddly enough, that's the same for many amateur astronomers. Also, probably professionals, for that matter. He caught a brief glimpse of the Galilean moons of Jupiter and was hooked. After some introductory reading, he now spends countless hours volunteering at various organizations such as Northwest Jersey Amateur Astronomers and here as president of United Astronomy Clubs of New Jersey. And even with all that drain on his free time, he still manages to frequently find himself outside at night in awkward positions, freezing cold, seeing neat stuff in the sky. And with that, Paul.
Hello, everybody. And bang, whoosh, zoom. Thank you. And thank you, Kim. Just a quick poll. Who knows or thinks they know what this talk is about from the title? It's big. Yes? Nope. Good guess, though, because it's onomatopoeia for those sounds that a rocket ship might make, but it's actually about the Big Bang. So we're going to talk about the big. Yeah.
Yeah, the
Thank you
online
for the
guess was
enthusiasm.
about the moon, like bang zoom to the moon, Lucy.
Yeah, that's another good one. Throwback. So it's about the Big Bang Theory. It's slightly irreverent. That's my addition to it. Book report on the first 3 minutes, which is a very good amateur. It goes into the science kind of deeply, but it doesn't have a lot of math in it. So highly recommend that book. Who's to blame for this? As I said, for any bad humor and any mistakes, I will take all the blame. But for all the good science, let's give this gentleman, Steven Weinberg, a loud shout out. The book is actually called The First 3 Minutes, A Modern View of the Origin of the Universe, and it's an updated edition. Originally came out in 1977, so we're talking 50-ish about almost 50 years ago, and but it has been updated with more recent information. As you know, science is a constantly moving target, so it's good to see that it was updated by the author for current information. All right, so here is the list of things we're covering. First, we're going to talk a little bit about the author because he was quite an accomplished gentleman. Quick review of some science concepts, expansion and redshift, cosmic microwave background, a few select moments in time, and then some afterthoughts. And I do just want In case some of the youngins get wrestling, this is Science Dense. So if I understand, please show them the interesting stuff in the telescopes. If it, I will not take offense if you need to move on to something a little bit more entertaining. All right, let's talk a little bit about Steven Weinberg. Born in May of 1933, and he died relatively recently in July of 2021. This is him here. And he was standing with an interesting group of people here, especially this person. That's Queen Beatrix of the Netherlands. She was queen at the time. She is still with us, but she abdicated for her son, who was then the prince. And so he is now king, and she is, I don't know what her official title is currently, but she is no longer queen. A very abbreviated list of Steven Weinberg's professional achievements. He is a PhD. I do not call him doctor. This is how he is known. I saw on the book how he referred to himself, so I am just using Steven Weinberg as his name, but he does have a PhD. He got that PhD from Cornell University. From Princeton University in 1957, and his undergrad was from Cornell. He did a lot of original research and theories in particle physics and physical cosmology. He shared the Nobel Prize in Physics with Sheldon Glasgow and Abdus Salam in 1979. And if I mispronounce those names, I apologize. And that's, of course, the Nobel. These are some of the Nobel laureates from that year with Queen Beatrix. He has numerous other awards in sciences and for science advocacy. He was a researcher, part of the faculty or lecturer at Columbia, Berkeley, MIT, Harvard, and the University of Texas Austin, so quite auspicious. 15 books on science, science communication, and science philosophy, very well published, and he has multiple scholarly and popular articles. So you could say a giant in the physics world. Okay, so yay. Let's get to the science. Let's review some science concepts, and 100% guaranteed or your money back for all that huge investment you made for tonight's visit. We are 100% guaranteeing almost no equations. All right, first a little review on particles. Particles that move fast enough when they collide will overcome intranuclear forces and are annihilated. Okay, new particles are then created from the resulting energy. So when you think of a particle collider and you think that they're counting the various parts of atoms and particles, and they are identifying them and all that type of stuff, you have maybe in your mind a standard collision like we would experience it up here in the big world, that it shatters into little pieces, and that's completely wrong. Okay, it goes to energy, and from that energy it reconstitutes as particles. And right here, E equals mc squared, you can think of it this way. If you remember, if you add a third line to that particle there, E is equivalent to mc squared. That's maybe a way of thinking about it. I'm sure the particle physicists will tell me I'm wrong, but maybe that's just a way to begin to understand it. Energy and matter are not really different from each other. Matter is sort of a form of energy. So it's an equivalency. And that's why when you smash particles together, it creates energy, and from that energy, the particles happen. Particles are created in matter-antimatter pairs. The photon, if you remember, the carrier of light, is a particle with zero mass. It mediates the electromagnetic force. Okay, all things electromagnetic, including light, involve photons. Electrons are called leptons and are small and small mass. So leptons is a different type of particle from a photon. And then finally, protons and neutrons are baryons made up of quarks. So again, another type of particle. They are larger and more massive than electrons are, the baryons. And then finally, neutrinos are not another type of particle, but a different type of lepton. Neutrinos are leptons that react with baryonic matter only extremely weakly. That means that a whole bunch of them are passing through you right now, and you'd never know. We wouldn't be able to detect it. We don't know because they just don't do anything as they pass through. All right. Oh, and this title would have been a lot more make a lot more sense if I had remembered to include a slide previously to it. So that's a failed joke right there. Sorry about that, everyone. So right here is let me make sure I get the name right. The Young's double slit experiment. The Young's double slit experiment has rays of light coming this way into a double slit. That double slit then reacts here on this let's call it photographic medium. This photographic medium here then shows this pattern right here. It's called an interference pattern, and it happens to waves. So this is a reminder that particles are weird, and they act sometimes like particles, but also sometimes like waves. And this is another example of an interference pattern. Black here, lighter here. Just cheating and looking ahead. Okay, more about light. Light can be, if you remember also that light can be red-shifted. If you can see these, each of these spectra are an example of some sort of compound. And what's happening here is light's hitting that compound, and then the electrons like that light, and then the light gets absorbed by those electrons, and then they're irradiating that light once they get kicked up, say, a notch, or an orbital, one might say. They get kicked up an orbital, and then they come back down to their original state. They'll give off that light again. Okay, so the light is absorbed, and then the light, the compound element goes from its natural state to an excited state, and then the electron comes back down to the natural state, and it's the light's re-irradiated. The difference, and why there's a black line there, is that the light has a source. It's between me and you. It's beaming right at you, but when the electron gives it back off, it goes in a random direction. So the light's no longer beaming at you, and that's why it appears dark to the observer. Does that make sense? That's how we tell, for instance, hydrogen is hydrogen when we look at its light. Oh, and the important part here, red-shifted. Okay, light can be red-shifted if it's going away from us, blue-shifted if it's coming towards us, the source object. So, red-shifted, you can see it's the same pattern. It's the same stuff, right? Two lines really close together, one line, two lines a little further apart, right? It's the same stuff. It's the same lines, except the red-shifted spectrum is shifted to the right, and the blue-shifted one is shifted to a little bit left. And now you understand why it's called redshift. Okay, the spectrum, same stuff, same lines, shifted one way or the other on the diagram. All right, so a little bit more about light. Light can behave both like particles and waves. Light from objects in space can be collected and analyzed. Their spectra apparent from luminosities and can be directly measured. Similar to sound waves, light is subject to the Doppler effect from relative motion, the redshift. Redshifted light is lower frequency, longer wavelengths from objects moving away, the observer away from the observer, and is less energetic or cooler. Less energy means cooler. More energy means hotter. Blue shifted light is higher frequency, shorter wavelength from objects moving towards the observer, and is more energetic. Visible light is a small piece of the electromagnetic spectrum. So gamma rays, X-rays, radio waves, infrared waves, all part of the same thing. They are all light. Light is like they are like light. It's the same stuff. We just call a very small section of that broad spectrum light. The fastest anything, including light, can travel through space in a vacuum is c equals almost 300 million meters per second, or approximately 671 million miles per hour. That's the speed limit of the universe. And I wanted to go back here. Let me see if I can find it real quick. All right, so we talked about the dual nature of light here. We talked about waves or particles. All right, and has everyone here heard of the concept of Schrodinger's cat? Yes? All right. How many people heard, oh, well, the cat is somehow gets a condition of unlife in a black box, and we don't know, because we didn't see it happen in that black box, whether the cat is alive or dead, and that explains why light is a particle and a wave, and that completely explained it to you, right? No, yeah, exactly, humph. All right, not the whole idea of that thought experiment is that it doesn't make sense. That cognitive dissonance, that man, that I have no, that doesn't make sense to me. I have no reference to that at all. And that's exactly the point, because this concept of the dual nature of particles is called quantum superposition, and it only happens on very small particles, and there is no analogous situation up here in the big world. So it's not supposed to make sense. It's supposed to get to you that, oh, it's a weird thing that I have to think about. It has a dual nature. It is not one or the other. It is both. And that's some of the weirdness of particle physics. Sorry I skipped that part. Okay, we're going to take a poll here. What are these things? I gave you a chance earlier, so I'm going to give other people a chance, but thank you. Yes, sir. Galaxies. Very good. These are all galaxies. And I want to show you here this bonus material, and man, this night is just, this lack of night is not helping us see this here. But this is M101. This is M101 here. Yeah, this is the arm right here. You guys are probably having real difficulty seeing it out in the audience, our live audience. I apologize. This arm here with the nebulosity right here, and it's spiraling inward. Right here you see this, this fuzzy spot. This is the same arm. Nebulosity right here, fuzzy spot, but there's something else right there. What's that? That bright spot right there. You might have heard about this in the news. This is M101. This is my picture I took up here about 3 weeks ago. This is about a week ago. Maybe it might be an additional week, I forget. But this is before and after the supernova that was found in M101. And this right here, ladies and gentlemen, is a supernova taken up here at Jenny Jump. Okay, but correct, they're all galaxies. And Let's talk a little bit about galaxies. In 1750, and now we're actually into some of the arguments about why the Big Bang is the Big Bang. And I want you to pay attention. Don't get too lost in the details. Don't worry about the details. The argument itself is rather simple. The details, of course, are very sciencey. So you can just sort of like sit back and appreciate the details as details, but understand the argument. That's the important part. In 1750, Thomas Wright proposed that the Milky Way was a flat slab of stars in which our solar system resides. So that long ago. In 1775, Immanuel Kant proposed that some of the nebulae that astronomers observe are actually circular disks similar to the Milky Way. So we were thinking galaxies were different from just something we see up in the sky that was a part of our own locality. We were thinking that it was something distant and different quite a while ago. The widely accepted Kant's ideas of the universe full of galaxies were debated for the next 150 years. In 1923, Edwin Hubble observed the Cepheid variable stars in Andromeda, and using previous work from Henrietta Swan Leavitt and Harlow Shapley, proved that Andromeda was its own separate galaxy and not a nebula in our Milky Way. So we had data to prove those theories that say that there are other galaxies, that our locality is just not one thing. It is many galaxies spread throughout the entire universe. Hubble's original estimate that the Andromeda galaxy was 1 million miles away. The modern estimate is it's approximately 2 million miles away. 2 million, light years away. 1 million light years away and 2 million light years away, not miles. So what does that mean? Okay, again, we can get into the science details, but we want to appreciate the argument. The argument's rather simple. Astronomers weren't sitting around waiting for galaxies to be quote-unquote discovered, or the math to actually prove that theory that galaxies were different, separate, and throughout the universe. They had since the mid-19th century, and among many other things, were investigating these things. Astronomers had been measuring spectral shifts of astronomical objects, including the previously suspected, now confirmed galaxies. Okay, so we already had the numbers. They were ready to go, waiting for it to be proved. It was quickly noticed that with only a few exceptions, all galaxies were red-shifted. Hubble announced in 1929 that he discovered that the redshifts of galaxies in all observed directions increase roughly in proportion to their distance from us. What does that mean in English? It means that the further away they are, the faster they're moving. This became known as Hubble's law, and its accepted current thought on the value of the Hubble's constant is between 67 and 77 kilometers per second per megaparsec. Don't worry about the units. Big numbers, big distances, and there's a relatively tight agreement, but there's still some why are they different when we measure it? Things going on that they're trying to figure out. But we have an actual mathematical construct, and you notice that it's like a constant. So what does that mean? A straight line relationship. The further it is away, the faster it moves away from us. So we can make some conclusions based on that. Here are the implications. The universe is not static, it is currently expanding. The universe is homogeneous and isotropic. This is the cosmological principle. That means it's the same everywhere, whatever direction you go, on a big scale. we can now play with the universe's time coordinate in our minds. Okay, so if the universe is expanding because things that are further away from us are moving faster, and we can predict that in the future things will be further away from us than they are now, right? That makes sense. Well, here's where it makes more sense for our topic today. We can also rewind the time. Go this way with it. And if we rewind it, and instead of things getting further away that way in time, this way in time, everything a lot closer together, right? If you go back far enough, the implication might be that things were really close together way, way, way back. Very simple argument. Dr. Weinberg introduced Friedman's critical density and wrote some about the universe's fate. We're not going to talk about the fate of the universe, the heat death of the universe, all interesting subject, but we're worried about the beginning, not where we're going at the end. Maybe Daniel will talk about that one next. All right. If you hit the rewind button hard and long enough, almost all the way back to the beginning of time, almost all the way back to the beginning of time, you can see that all things must have been a lot closer together than they are now. That was the conclusion we talked about, a very simple conclusion, based on all that cool, difficult science. The implication, I mean not a lot closer, but a lot closer. I mean, you really don't understand. It's really, really, really close. It's weirdly close, as in what we talked about early, particle physics level of close. And from an infinitesimal and hypothetical point before particle physics close is maybe when it all started. We now call this theory the Big Bang. Okay, so that's the theory in a nutshell. Very simple concept with some really cool science behind it. We don't actually, and just so I say here, before particle physics close, we're not going to talk about what it was before we have physics to actually describe it. Physicists and everyone are going to say, we don't know. They might have some suppositions. They might have their own personal hypotheses about those, but we just don't have the physics to describe that. So we're just going to pretend that that issue doesn't exist because we can't know. We don't have a model anyway currently that tells us anything meaningful about that state. All right, so let's talk about, we're talking about science here, so let's talk about some corroborating evidence. Let's talk about the CMB, the cosmic microwave background. Did you know, and some people might know the story, the cosmic microwave background, and let me see if I can find a picture of these guys, might even know about these guys but at Bell Labs, but we'll go back here. Theoretical physicists predicted the CMB over 10 years before its discovery. In other words, the prediction happened first, and that's important from its validity of the argument, right? It was postulated from exploring the particle physics of the early universe. However, they did not predict its importance as corroborating evidence of the Big Bang theory. So experimental verification lagged its actual discovery. They didn't think it was, they said, hey, this dropped out of the math, isn't that cool? And they moved on, and no one really pursued it as something to look at. However, once upon a time in New Jersey, these gentlemen were fooling around with radio equipment, very sophisticated radio equipment. In 1964, Mr. Penzias and Mr. Wilson, Mr. Wilson's on the left, Mr. Penzias is on the right, worked for Bell Labs in Homedale and were commissioning a radio telescope for a survey of the Milky Way. They were troubleshooting sources of noise in the signal from the receiving system. So they have this new thing, they're commissioning it, making it work right, and they get this signal that they couldn't figure out what it was. Where's this signal coming from? We cleaned everything, we made sure everything was working okay, but we're still getting a signal. They were measuring in the microwave wavelength at 7.35 centimeters. They found a stubborn source of noise that didn't depend upon where they pointed to the equipment or what time of day it was. So that was something that made it special in their minds already. The signal corresponds to a excitation of electrons in a closed thermal system at a temperature of 3.5 degrees K. This is referred to as a black body temperature. Now, everyone now can buys your light bulbs, and it has a K number on it. That K number is the temperature of that light as a black body object. That isn't a K number, that's an actual temperature. So that's the temperature of the light. This, yours is typical, our light bulbs are, if I remember, something in the thousands of degrees K. This light is happening at 3.5 degrees K. Almost no K, right? Through colleagues, Penzias and Wilson were put in contact with physicists of Princeton who had theories about leftover radiation from the early universe, who were setting up their own experiments. Peebles and Dick and Roll and Wilkinson were some of these people. Penzias and Wilson ended up founding this leftover radiation that these gentlemen had theorized. They won the 1978 Nobel Prize for Physics for that discovery. Okay. But what is the CMB? We just talked about a bunch about the CMB. After the Big Bang, the expanding universe was very hot, very dense, soup of radiation and elementary particles. Matter didn't exist as it does now. It was energy and very few particles. Even though the universe was expanding rapidly, the mean free time between radiation and particle interactions was unimaginably fast. Radiation couldn't go anywhere. The universe was opaque. Okay, they talk about mean free time sometimes when they talk about something getting released from something else. Okay, so things were so dense and so packed. Think about like a pool of balls at McDonald's or something like that. Everything was just really packed together, and a little ball vibrating at the bottom of the pool can't get out to the top. That's a similar thing that was happening in the early universe. The radiation and particles were in thermal equilibrium and behaved like a black body. That's why we'll talk a little bit more about black body in a minute. The universe then cooled in thermal equilibrium until it reached around 3,000 degrees K. And then electrons bound to atomic nuclei and regular matter formed. And we're getting to it, almost at the aha moment. The universe's density dropped and became transparent, and the radiation was released. So it was a big ball of energy. The entire universe, big ball of energy, elementary particles, it cooled, regular matter formed, and all of a sudden all this extra energy, whew, just started traveling throughout the entirety of the universe. Okay, so it was released. The universe continued to expand. The wavelength of light expanded with the rest of the universe. It is redshifted and therefore cooled. So that energy expanded, and as you remember, red means cool. The red going in the red direction means it's getting cooler. So this energy that was released during the Big Bang started cooling, and that is the black body radiation we now see at 2.725 degrees K. Why do we know the Big Bang exists? Because we can see it. Why am I saying black body? Black body is these curves, and a lot of the work was developed by Max Planck, and Black body radiation, I'm just going to go over this curve real quickly here, this is logarithmic, this on this side, and yeah, on this side, and these two, and any curve that, any source of light or other electromagnetic energy that forms this shape curve is considered a black body. And all that really means is that only the temperature of that body is what is contributing to that measurement of energy. It's not reflecting energy, it's a perfect absorber. So all the energy that it's giving off is in the form of thermal energy. And here's an actual current picture of what we can see in the universe, or what they at least measured of the universe, of the cosmic microwave background. That is the Big Bang. Really expanded, very much cooler than it used to be, but that's an actual picture of the Big Bang. So corroborating evidence. So let's move on from those two facts. And the argument, again, rather simple. We have a picture of it, and you know, we can rewind the clock in our brains that if it's expanding, then it must have been smaller back in time. So a few ticks of the clock to determine the play. And a lot of this we will just go over quickly. We start somewhere very soon. As I said, we're not talking about the theoretical what happened before the Big Bang. We are just talking about the Big Bang itself. We start somewhere very soon after the Big Bang. It's kind of hot. It's about 100 billion degrees Kelvin in the universe. The universe is a soup of matter and radiation, and it is in a state of thermal equilibrium. The only matter that exists are the electron, the positron, neutrinos, antineutrinos, and the photon. The density of the universe is approximately 3.8 billion times of liquid water. Very dense. After 0.11 seconds have elapsed, the temperature is only 30 billion K at this point. The universe is a soup of matter and radiation, as in a state of thermal equilibrium. The only matter that exists are the electron, positron, neutrino, antineutrino, and the photon. Free neutrons and photons are formed and blasted out of existence. So neutrons, it's starting to try to form matter. Their ratios differentiate to 3 baryonic matter, I should say. 38% neutrons and 62% protons. The density of the universe is now approximately 30 million times of liquid water. Tick, another tick. Now 1 second after the Big Bang, approximately. The temperature is 10 billion degrees K. The universe is a soup of matter and radiation, and it is a state of thermal equilibrium. That one's going to appear in a lot of slides, you may tell. This red here one's important. The universe becomes transparent to neutrinos, and we'll go over why in a moment. Free neutrons and protons are formed and blasted out of existence. However, they happen at different rates to the rate at that they were being formed. So if you notice previously, it was 38% and 62%, and the ratio is now changing because one is getting destroyed way faster than the other. 24% neutrons and 76% protons. The density of the universe is approximately only now 380,000 times that of liquid water. After almost 14 seconds, the temperature is a chilly 3 billion K, electrons and positrons, blah, blah, blah. No, this actual one is new, sorry. Electrons and positrons are stable at this temperature. They begin to annihilate each other. So they're no longer being formed and going back to energy. They now find each other and destroy and annihilate each other. They destroy each other. Neutrinos previously freed are cooler than the rest of the universe. That was the important red one there. The balance of neutrons to protons is now approximately 17% to 83%. Some stable nuclei can now form. Helium and atomic weights above it, so all the other elements, are still suppressed. So hydrogen is forming, everything else isn't. 3 minutes and 2 seconds have now elapsed. The temperature is 1 billion degrees K. Electrons and positrons are mostly gone because they have annihilated each other. And the universe is now mostly consists of photons, neutrinos, and antineutrinos. The balance of neutrons to protons is 14% to 86%. Some stable nuclei can form. Helium nuclei can now form but are suppressed because deuterium, which is a necessary precursor, if you know your atomic equations, is still not stable. Okay, an intermission here. Let's take a quick breath. That was a lot of science very quick. Approximately 3 minutes and 45 seconds have passed. The deuterium nuclei are now stable. Helium nuclei form at a rate twice that of available neutrons in the universe. 13% neutrons to 87% protons. The temperature of the universe is now 90 million K. So no longer in the billions. So we're really starting to really get cool. And this number here, just let me double check. Yeah, this number here is our current concentration of neutrons to protons. Okay, after the intermission, another tick. 34 minutes now and 40 seconds have elapsed. The temperature is a chilly 30 million K. Electrons and positrons are gone, except for 1 part in 100 million. Okay, and that's a question in science to this day. Why we didn't make an equal amount of electrons and positrons and they just wiped each other out completely and we don't have a universe at all. Well, whatever the reason is, we're happy because we're here now and we have a universe, and so the electrons slightly there are just slightly more of them than positrons. Nuclear processes have now stopped in the universe. They just aren't happening everywhere in the universe. Nuclear particles are bound in mostly hydrogen or helium nuclei. It is still too hot to form stable atoms, though. They are all ionized. And the density of the universe is approximately, it's only 9% of liquid water. Still a lot more dense than the universe is now, but really not billions times or millions times the density of water. Okay, and the lights now begin to fade, so to speak, on our little play here. Not much interesting happens for the next 700,000 years. The temperature drops below 3,000 degrees Kelvin. The stable atoms are now possible. Free electrons and atomic nuclei begin to pair and make happy little atoms. We are now in what we see the universe very much the way it is, similar, the physics anyway, to what it is now. The universe becomes transparent to radiation. That's where the cosmic microwave background happened, right here. Stars and galaxies begin to form, and then another 10 billion years or so go by, and Dr. Weinberg writes his book, The First 3 Minutes. And we've come full circle. So afterthoughts, things to think about. A lot of dense science. Again, the argument for why the Big Bang exists is rather simple, but a lot of dense science went in to make those arguments. The cosmic neutrino background is as predicted at 1.75. So let's go back to those red things that I told you was important. We talked a bit about the cosmic microwave background. But something else got released. We talked about it. I told you right here it was going to be important. The universe becomes transparent to neutrinos. We talked about the transparency of regular radiation. We found the cosmic microwave background. But this thing got released. These neutrinos became it was the universe. The rest of the universe was transparent to neutrinos before the rest of the before all that radiation. So what does that imply? If it was released earlier and went through an expansion, it should be what compared to the cosmic microwave background? It's a temperature thing. It should be cooler because it expanded more. Okay, and here we go. Back to this slide. The cosmic neutrino background, as predicted, it's a cooler temperature than the CMB. The cosmic neutrino background, the CNB, is cooler than the CMB. Cosmic inflation and the CMB, so that's what I described here. Before the Big Bang, I told you we're not really going to talk about it. There are theories that it was a singularity before. We just don't have the physics to describe it. We can't. It would be a guess. Can't tell you what it was. The matter-antimatter asymmetry. I went over that on that slide. Dark matter and dark energy. Where does that play? Those are relatively recently made it at least into the public's awareness recently. Dark matter and dark energy play a role in the cosmic expansion. We talked about, I'm not going to go all the way back, but we talked about the eventual fate of the universe if we wound the time to the future as it expands. The universe could expand in a flat if there is just enough energy if there's enough gravity to enough mass in the universe, then that expansion that was happening could be pulled back together by the universe's mutual gravity, or it could go flatline, or it could expand. Those are the three possibilities. Well, we found now, and we've verified that the universe is accelerating in its expansion, and that dark energy plays a big portion of the role. And then finally, I did say that maybe Daniel will talk about what happens at the other end of the time spectrum. What happens at the end of the universe? The heat death is one of the things where there's just not enough energy to do anything. Completely nothing. No energy to run clocks. We don't know what time it is. Time doesn't even exist if nothing's changing. So just a whimper of an end to the play. This is the I did say that the author, Mr. Weinberg, or Dr. Weinberg, he put in some times and this is the actual current thought of what is happening as of very recently. The timings that he has in his book are let's see, that's 25 years old. So this 375,000 year number might be slightly different. This number might be slightly different. This is the current numbers, but all the steps are basically the same. Okay, and before we're going to go to a Q&A session, and I'm just going to nip this one right in the bud. Didn't the JWT break the idea of the Big Bang? No, just no. There was early identification of anomalous results relating to the size of early galaxies when the new data started coming back from the Space Telescope. The size of the early galaxies were estimated originally incorrectly. So they identified this anomaly, and they said, hey, this is a head scratcher. We can't figure out why these galaxies are bigger than they should be in the early universe. The mistake had to do with light extinction and the application of photometric versus spectroscopic redshift. I'd suggest reading about that stuff if you're interested in some of that. The current estimates of the galaxy's sizes fit the CDM model of galaxy formation. In other words, they used the photometric method. They should have, or people had since used the spectroscopic redshift, and those the reason to use one versus the other is that the photometric method is very sensitive to light extinction, and if you have to estimate the light extinction, how much the light gets absorbed by gases and stuff like that in the universe. You have to estimate that very well for this number to make sense. So they use this number that isn't sensitive to this data, and they got results that are consistent with the current model. So the James Webb Telescope did say that we have to be careful how we measure this stuff. It didn't say that the Big Bang doesn't work. I'm not going to go into it, but there may be a little bit of the media wanting to create controversy, maybe some people who don't understand the science very well talking about like that they know what the science means. Just to help combat motivated reason, there is just philosophically, Harry J. Frankfurt has a small book called On Bull Stuff. Might need to, when you put that in the internet, you might need to modify that word a little bit. And then also The Skeptic's Guide to the Universe by Dr. Stephen Novella and others both help combat a little bit motivated reasoning and illustrate some of the pitfalls of motivated reasoning. Okay, everyone, join an astronomy club. Stay safe. Enjoy your evening, and thank you for listening to that very dense topic.
All right. Thank you, Paul. Thank you for everyone who's joined us. We are doing a Q&A session, but first things first. As always, the safety briefing that everyone hates, but I'm still going to do it. If you need to use the restroom, it is the porta potty in the back to my left and your right. I also have a little museum and gift area in the door to my left, outlined in red. Also to the left, each of those sheds is an observatory with a roll-off roof that does house a telescope. Unfortunately, it's very cloudy. Oh, look, a bat. Sorry, it got sidetracked. When it gets this dark, you get bats instead of squirrels. But that's besides the point. When we go to leave, it'll likely be darker than it is already. We are using our headlights because we like not running people over or getting run over ourselves. However, if we do use flashlights or any other source of light to move around, we will keep those pointed towards the ground just so we don't accidentally blind people. No one likes flashlights in the eyes. All right. So, what's going to happen for those of you who are here who have questions? When I call for a question, you're going to raise your hand, wave it around, and keep it like up, because as I'm walking to you to hand you the microphone to ask your question, I will lose you because I become like a T-Rex, and my eyesight in the dark is based off of movement. It is what it is. I can't read the screen with my distance glasses, but I can't wander the crowd without them, so that's my life. All right. So I'm going to open it with an online question. What happens if a lot of the info in this presentation from that book, if the book is a mistake and your humor and mistakes are actually the correct option?
That's very unlikely. I'll entertain it for another universe, but not this one. I would, as I said, Dr. Weinberg there is a very Nobel laureate, I would lean to accepting his interpretation of things and steer away from any mistakes that I might have made.
Hey, it's still nice to think about. Like, hey, maybe in an alternative universe, I'm actually the correct one.
Yeah.
All right. Is there a question out here? I hear crickets.
Quickly, move on to the next question online.
Aw,
Thank you for
no
being
fun.
an easy crowd tonight.
Basically, I just want to see some tough questions for him, which I know there are. Um, you were you were talking about reconstituting the universe. If you add water to reconstitute the mix, do you get cake?
Yeah, it's an interesting soup. Interesting to see the ingredients develop.
Oh, soup, not cake.
But it is a soup is a really good explanation of those plasma and those theories of the reason why Dr. Weinberg got involved with this, as he was a particle physicist. But why is he doing cosmology and things about the universe, right? And that stuff was how matter is made. It is like a soup, isn't it? It's like those are the ingredients of what everything is made of. And that's why we're colliding stuff together in a collider to better understand how the universe was made, because that soup is where all that science comes from. How particles are made, what the early universe was like, what the timing of all those things are, what the energy required to make all those things are. And that's where we get these times, this data that allow us to understand what happened. That's why we're doing all these particle physics research. Really cool stuff. And if you read about particle physics and you don't mind learning some really weird stuff, they have some good introductory courses to help you better understand particle physics. So, as a layperson.
All right, I got a question out here.
It seems that the few moments after the Big Bang were very dangerous. What about the effect that two particles collide in the super collider? Could there be any catastrophic effect on those?
Two things I want to say about it. There is a guy who famously stuck his head in a particle collider while it was on. He lived, had some head trauma associated with it. I've heard tales of how much energy is involved in modern day particle colliders, and it's equivalent to something like two battleships going full steam at each other, the collision. So I wouldn't recommend being anywhere near particle, the stream of a particle collider. Secondly, are anyone familiar with industrial safety? Raise your hand if you are. A little bit. So you know what a HAZOP is? I would have loved to be on the HAZOP for when they built the first particle colliders, and they do them, and they do involve things like, can we destroy the universe by doing this? So interesting HAZOP to be on, wouldn't it? It's a matter. It's a matter of. I don't think that they actually thought, but the HAZOP you bring. Could this happen? And what would we? If it could? Should we stop or should we? So they thought about it. It's not like they just let's throw them together and see what happens, right? They actually thought about it. So good question.
Yep. Let's face it. Anything thrown with or propelled with enough velocity is quite dangerous. They run into that problem with the International Space Station all the time. The next online question is actually a good point. It goes back to the
Schrodinger's cat.
Cat comment. Doesn't light kind of behave like a neurodivergent person? They mask and behave the way you expect them to, when you're watching them. So if you expect them to behave like a particle, they're going to be a particle.
Yeah,
if you expect a wave, they're going to be a wave.
Yeah, I cannot. I can't comment about the psychological aspect of that. I am not qualified to do so. However, yes, the at one point they thought that there was intelligence, some sort of intelligence, or it was related to our own intelligence of the observer, that when you watch these through experimentation, when you watched it and expected a particle to behave like a wave, it behaved like a particle, and then when you expected it to behave like a particle, it seemed to know what the observer wanted from it, and it did the opposite thing. And no, what ends up happening is, and I don't know the physics at all, so I can't help you with that. I don't know any of the quantum physics or anything like that. Somebody who is who's trained in that stuff could tell you. But the waveform collapses at a certain point, and it shows one or the other. They exist as both. It's a very weird world, and you just have to, us as lay people, just sort of have to accept it, maybe get familiar with it and understand it a little bit more, but it comes down to the mathematics of why it's happening that way, and that is some pretty hairy-brained mathematics.
So while I'm walking to get the next question, do you actually want to put up that slide with the pictures of M101?
M101.
Just because now it's dark and you'll actually be able to see a little bit better.
I can show you M101. I'm glad to show off my hack
right.
images.
And while you're doing that, here's the next question from our in-person audience.
Two things at once. I can't guarantee I can manage that.
You said that what happened before the Big Bang is kind of blind to the physics, but you mentioned that there has been some theories. Can you state the most known,
yeah.
or the two most known?
I think the only one that I'm very familiar with is that it was a singularity, and I would have to draw a little issue with your question. Only that let's talk about the difference between what we as lay people call a theory and what scientists call a theory. A scientist will call a theory after it has been vetted by many scientists, has data that you would ever want to see, and the error bar on the or the p-values that it could be a random effect are vanishingly small. So we would call it a certainty, and scientists would call it a theory. So scientists are very careful when they call something a theory. So I wouldn't call it a theory. In this point, it's conjecture on their part, because they can't support it with mathematical or data or with calculations, and therefore some of the conjecture, at least one of the conjectures, is that it was a singularity. And here is the...
I think that kind of takes me back to what is it, 4th or 5th grade science class, where we go through and learn the scientific process, where first you have a hypothesis.
Let me try
hypothesis. I can talk too.
Yeah, hypothesis, and there's back of the envelope thinking even before you reach a hypothesis. And these people's back of the envelope thinking, we wouldn't even, these are experts who've got doctorate degrees, and have 40 years of experience in the field. We wouldn't be able to understand their idle thoughts on the subject, I don't think. There, that worked.
All right, perfect. And the reason why I had you actually pull this up, besides actually having a better view now that it's darker, is because the next online question is, at what point in time do we expect the supernova to reduce in brightness again?
From someone approximated from when they found it 30 days. It was what, 2-3 weeks ago. So we're getting, but I saw it last week. One of our members had it up on a setup similar to what I was doing here, and and could see it just fine on his EAA. Right here, again, this is the arm, a little bit nebulous at the tip there. You can see the arm right there, and you can see this fuzzy spot. This is the same arm, nebulous at the tip, going into the center. There's that same fuzzy, but right here is a brighter object. That brighter object is the supernova in that galaxy.
All right, another question from our audience out here. Again, you might have to raise your hand and kind of wave it about because I am a T-Rex. Perfect.
Question: those are photos that you took?
Those are photos I took. This is like a week before and a week and a little bit after the supernova. I don't think my see the
Your
red dot?
laser is not high powered enough. Oh,
See
maybe
the
it
red
is.
dot? The first one I took on that in that observatory on my camera. The second one I took on my personal scope, which I bought up here, and you can see a little bit how it's black around the edges, and it gets a little trapezoidal. However you say that, it's a trapezoid. And you can see this one's a trapezoid. That's because my mount, this one's more square. My mount is an equilateral mount, an equatorial mount. This one is a fork mount. And for why that makes a difference, I refer you to one of my earlier talks earlier in the year. But so that's why I switched scopes.
All right. So our next question has to do. So everything is running away from us really, really fast. Is that why we are unlikely to find other sentient life? They looked at us and said nope, and just.
It's not because of their desire to avoid us, though I wouldn't blame them at times. But certainly there is a point where in the far distant universe where we would lose a lot of our ability to observe the universe. Only our local group will be, they call it, of galaxies would be close to us. The rest of the universe would be unobservable. And there is actually currently a spherical wall in the universe and our side of it is called the observable universe, and on the other side of it, again, the scientists posit that the universe just continues, one of the posits, or that continues to go, but we really don't know because we can't observe it. So we can observe the universe on this side of the wall. On the other side, it's moving too fast and is too far away from us for us to ever see that light being generated from those locations.
All right. Another question from our audience. Perfect. Thank you, John.
About approximately how big do you think the universe would be before the Big Bang?
Yes. Again, before the Big Bang, you can make up your own posit about that. I don't know that we have an answer. Again, the physics just don't support what. These people that come up with these theories, etc., very smart people. I'd listened to them before myself. So someone had posited a singularity before. I don't think the other is that it's just been shrinking and shrinking and shrinking and is still the further back you go in time, the further it shrinks. Some say that the meaning of time has no meaning once you get far enough back. Who knows? We don't have physics to support it. It's all good as far as a theory, as far as what a layperson would call a theory, what scientists would posit.
All right. So I do have 2 more questions online because the third one, actually, I think we kind of just answered that. Yes, eventually there is an argument we'll no longer be able to wait to get to other solar systems and galaxies because they're going to be that much farther away.
Yes.
So I'm going to put out a last call for online questions. And is there another question from our audience here? All right, so our next online question, oh, please don't disappear on me, actually, is more of a comment about the when you were going on about how close things are. Is it close like a girlfriend trying to crawl inside of her significant other's skin for warmth? Close.
uh, yeah, I'm going to take that inappropriately seriously. Things in the quantum world, even space itself, break down. And I think there are some theories that space itself is quantized. So things are unimaginably close, right? We talked about Schrodinger's cat, and maybe that was a thought experiment to evoke cognitive dissonance. Well, again, this closeness that we're talking about, things below the Planck constant are unimaginably close, very difficult concepts, and nothing that we experience up here in the big world is like these distances.
And to answer the question I heard yelled out from the audience, no, that was not a question put out by my boyfriend, actually fiance now. So,
congratulations, Kim and Chris.
Thank you. All right, was there another question out here? Perfect.
What do you think about the theory where there would be all power for being in the fifth or sixth dimension that would have created something like this?
Yeah, I'm going to leave that question on the table. There's enough room, I believe, my personal belief, and this has nothing to do with anything that we've presented or anyone else's opinion. So I want to say my personal opinion is that there is room enough. Life is complex and difficult enough. There is room enough for both philosophy and for science. So I'm just going to leave that one there. Thank you for the question.
All right, so I have this next question, and it's kind of tongue-in-cheek, and the question after that is actually a follow-up based on that. How long would it take to microwave a Hot Pocket in the cosmic microwave background?
Yeah. Long time, again, I'm being pedantic and overly serious. A long time because we would have to wait for Hot Pockets to be able to exist before we can microwave it in the early universe. But obviously extreme temperatures, very impressive, and they would cook a Hot Pocket very fast.
The follow-up question to that was, would the Hot Pocket be like the normal ones where it's lava on the outside and you still have a chance of an ice block on the inside somehow?
Yeah. Yeah. Maybe there's some physics experiments that can be done in the center of a Hot Pocket. It certainly does get hot.
You put the darn thing in the microwave for 10 minutes. It shouldn't have ice in it in the middle anymore. Anyhow, so it looks like that did exhaust our online questions. Were there any more questions from our audience in here? All right, with that, I want to wish you all good night. I want to thank Paul for another wonderful talk. And for our audience online, do hit those like and subscribe buttons so you get notifications when we go live again. And you guys also can do the same. With that, enjoy your night.
Thank you, everyone.